Welcome back to College Algebra. In this video, we're going to be talking about polynomial functions. We actually talked about polynomials back in Chapter 1. Or no, the review chapter, even before Chapter 1. And polynomial functions is basically just building on that material. So, what is a polynomial function? A polynomial function is a function where your function equals a polynomial, just as we defined them back in Chapter R. So it has a bunch of terms where all of these coefficients out front are real numbers, and then all of these powers on the variable are whole numbers. So 0, 1, 2, 3, 4, 5, 6, 7, etc. I said positive integers. That's not actually correct. Should be non-negative integers. Because it could be 0. A sub 0, that x term has a power of 0 in it. Alright, properties of polynomial functions. Domain is always all real numbers, negative infinity to infinity. There's no division here, so no possibility of dividing by 0. There's no roots, no possibility of roots because there's no fractional exponents. They have to be integers and non-negative or whole numbers. So there's no possibility of imaginary numbers. Domain is negative infinity to infinity. If you look at the graphs are all continuous. They have no holes or infinite jumps. We'll look at asymptotes in more detail in the next couple sections. And if you look at the ends of the graph, so if you look at, say, as it goes off infinitely to the right or infinitely to the left, the graph will begin to look like the graph of the leading term. So, if you zoom out far enough on this graph, negative 3x to the fourth, plus 2x cubed, plus 13x squared, minus 8x, minus 20. Because as you get into large x values, this power will be so much larger than all of the other terms combined. Eventually, this function will start looking like this function. So this function is what our book calls the end behavior. Honestly, in other textbooks, they just really talk about whether it's going up as it goes to the right or down as it goes to the left or whatever it's doing. Which, honestly, that's just based on if it's an even power, it has both arms going up or both arms going down. If it's an odd power, one's going up and the other's going down. And you can talk about negative or positive. But honestly, let's pull up the graphing calculator and look at this real quick. So here we go. If I plug in negative 3x to the fourth to the fourth plus 2x cubed plus 13x squared minus 8x minus 20. And if I look just at the standard window to start off, oh, I need to plot the other one. Negative 3x to the fourth. They don't look that much alike in this area, but let's zoom out. This is just negative 10 to 10. Already, it's kind of hard to tell them apart. Let's make my y's go a lot deeper than that. Let's say negative 400. And you see, the more and more you zoom out, the more and more they look like each other. That's going to be true in general. So continuing on, let's have a definition. A zero of a polynomial function is an x value where the function equals 0. Remember, this is our replacement for y, so it's where y equals 0. So it's actually going to correspond to an x-intercept if it's a real number. If it's not a real number, it won't show up on the graph at all. But if it is a real x value, a real number x value, there'll be an x-intercept there as well. And that's one of the easiest ways to find zeros. We're going to talk about multiplicity. Multiplicity of a zero is the number of times the corresponding factor appears in the factorization. So here I give you a quick example. If you look at this polynomial function, x squared plus 2x plus 1, it's a quadratic function, which we looked at in previous chapters, but a quadratic is just a second-degree polynomial function. This factors to x plus 1 squared, so this has a 0 at x equal negative 1. And notice the factor has a power of 2. That means the multiplicity of this 0 is 2. Why is that important at all? Well, it actually affects the graph some. If you look at a graph here, two graphs. I'm going to plot what we just did, x plus 1 squared. And I'm going to plot x plus 1 times, let's say, x minus 2. So this has a 0 of negative 1 with a multiplicity of 2. This has a 0 of negative 1 with a multiplicity of 1, and a 0 of 2 with a multiplicity of 1. If you look at the graphs, oh, I forgot to change my window. Let's see, Z standard here. There. Alright, notice what happens at the 0. This is x minus 1 squared. X plus 1 squared. And you notice it doesn't cross down below the x-axis. It just bounces at its 0, at its x-intercept, and then just goes straight back up. Whereas the other one crosses at the x-intercept, and then crosses at the other one as well. Well, you can actually tell whether it's going to do that by looking at the multiplicity. If it has an even multiplicity, like x plus 1 squared, it will bounce at its 0. If it has an odd multiplicity, like this one and this one for this function, it will cross at the 0. So that's a useful thing to know for graphing. Gives you a quick idea of what the graph's going to look like with a minimum of effort. One more bit of theory, and then we'll go into exercises. And this is what I was talking about before with multiplicity. The multiplicity of a real 0 affects the graph, and that the graph will cross the x-axis if the 0 has odd multiplicity, and it will touch the x-axis but not cross if the 0 has even multiplicity. We're going to use these conditions to answer our first set of questions from the text. These conditions are all equivalent, so they're if and only if statements. If one is true, all of the others are true. If one of them is not true, all of the others are not true. If you have a 0, then if it's a real number, that's an x-intercept. We already talked about that. But this is a new one. X minus r has to be a factor of f. And that's really the one we're going to use a lot. So, for example, x squared plus 3x plus 2. If you find its zeros, that's x plus 2, x plus 1. So x equals negative 2 and negative 1. What this is saying is, if you look at these zeros, negative 2, the function they came from has to have a factor that's x minus that 0. And x minus negative 2 is x plus 2. There it is. It has that factor. X minus negative 1, x plus 1. It's right there. Similarly, if I had the zeros of, say, 3, 4, and negative 1/3, I would have to have factors in my function of x minus 3, x minus 4, and x minus 1/3, so x plus 1/3. There's no way to have these zeros in a polynomial function without these factors. That's what this theorem is saying, and that's what we're going to do in our first set of exercises. So this is problem 44. We're going to form a polynomial function, the zeros and degree given. So like we said, I'll call this one f. I'll try and call the next one something different. You start off with the zeros. If negative 2 is a 0, x minus that has to be a factor, so x plus 2. If positive 2 is a 0, x minus that has to be a factor, so x minus 2. If 3 is a 0, x minus 3 has to be a factor. This already has degree 3. If I multiplied it out, I would get a third degree polynomial. So this is fine for an answer. It's not the only answer you could get. You can't have any more x's, because if you have any more x's multiplied, it'll be a fourth or fifth degree. But you could put a coefficient out here, like 3 or 17 or 1/3 or something. I'm not. It's just simpler if it's just 1 there. Because this is perfectly acceptable for me, like if I'm giving you a test or something. But the homework is finicky. It generally expects you to simplify, i.e. multiply all this out. So I mean, we can do that. It's not going to take super long. It's just basically an R4 problem 5 chapters later. But if we multiply this out, we can see what the final function would look like. So I'm going to multiply these two first, the x plus 2 and the x minus 2, because I have a plus b and a minus b. And it is a super fast multiplication formula if you remember it. A plus b times a minus b is a squared minus b squared. So this is x squared minus 4 times x minus 3, which is x cubed minus 3x squared minus 4x plus 12. So that's our answer. If I had multiplied by a coefficient, it would basically just be this multiplied every term by some number, whatever that coefficient turned out to be. Let's look at 55. This is slightly different. Not only do we have zeros given, we also have multiplicities of those zeros, and we also have a point that our function has to go through. We start off with the zeros like before. I'll call this function g. If negative 1 is a 0, well then x plus 1 has to be a factor. If 1 is a 0, then x minus 1 has to be a factor. This has multiplicity 2, so that means I have a square on that one. This also has multiplicity 2. So this is a fourth degree polynomial. Add the multiplicities together and you get the degree. But we need this to go to 45. And right now, if I plug in negative 2, g of negative 2 is negative 2 plus 1 squared, negative 2 minus 1 squared. That is negative 1 squared times negative 3 squared, which is 1 times 9. Now, that is 9, and I need it to equal 45. Well, that's no trouble, because like I say, you can just put a coefficient out here. You probably already know what it's going to be, but I'm going to show you the general process just because you might not know on a problem. And just plug this in this variable and you can solve for it. Because we know we want to get 45. So you just put a coefficient on the front. Then divide by 9, a equals 5. So our function is 5 times x plus 1 squared times x minus 1 squared. Again, they're probably going to ask you to multiply it out, so x plus 1 times x minus 1 is x squared minus 1. And I guess I have 2 of those, but I'll write them side by side. So that's x to the 4th minus 2x squared plus 1. So that's 5x to the 4th minus 10x squared plus 5. On this problem, I gave the instruction analyze and graph the function, because that's basically what it says, but let's go through what they're going to ask us to do when we analyze, because the book has very specific ideas of what it wants you to do. So first thing it'll do is ask you to find the end behavior. Now, end behavior is what the leading term would be. What will the leading term look like? Well, honestly, you can multiply this all out to find it, but it's really easy to find the leading term. In something like this where you have a multiplication, the leading term is just what you're going to get from multiplying all the highest powers. So x squared times x, we would get x to the fourth, and then a bunch of other terms. The end behavior is going to be like x to the fourth, which, by the way, x to the fourth looks like a parabola. So that's what both ends are going to do. It's going to go up on both ends. But the homework will generally just ask for this leading term. So that'll be it. Then it'll ask you to find the zeros and y-intercepts. So this is already set up very nicely to find zeros. If we set this equal to 0, this will tell us there's zeros at x equal 0, because set x squared equals 0, x equal 3, and x equal 1. Their multiplicities are 2, 1, and 1. And our y-intercept is at, well, I guess it's just going to be at 0, 0. You'd set x to be 0, so y-intercept at 0, 0. Whenever you have an x-intercept at 0, it's also the y-intercept as well. So, let's take a look here. Generally, I don't decide on my y-axis scale until I've looked at a few points. So we have, I might as well go by ones on the x-axis though. 0, 1, and 3. Let's bring up the calculator. So we have x squared, x minus 3, x minus 1, and I'm just going to look at the table for now. So we can see it goes up pretty quickly. That's probably good enough for whole number values. I'll probably still need one or two others, but we can see, I mean, that seems pretty reasonable. -1, 1, 2, 3, 4. Let's go by, might as well go by ones. There's no special reason not to. -1, 8. What does it do at 2? At 2, it's -4. I would like to know what it does in between these two. I mean, I know it has an even multiplicity, so it should bounce back up and come back down and cross, but I'm not sure how far it bounces up. So let's go into trace, and let's plug in something in there. So let's plug in 0.5, 0.3125. All right, that's about a little under 1/3, so that's about right there. And then I know at this one it's at like 4, it's really high up. Because we looked at the table and I think it said 48 there. Yeah. So it looks like this. It's zooming down, has a relative minimum there, comes back up, crosses, goes down at least that far. It might actually go a little bit further. If you want it to be more exact, you can find the local minimum and local maximums in your calculator. That's a job that can be fairly tedious in college algebra because you basically have to use your calculator for it, unless it's a very simple shape like a parabola. But in calculus, it's a very easy trick. So yeah, there's our function. Let's compare. Yeah, looks pretty close. The last thing it might ask you to do is it might ask what's the maximum number of turning points. I'll just make a note on this problem about it. Maximum number of turning points of an nth degree polynomial is n minus 1. So note, in our case, we had a 4th degree polynomial and it turned 1, 2, 3 times. N minus 1 is 3 times. It could have less than that. Like, for example, we looked at an x to the 4th function a bit ago. X to the 4th just looks like a parabola. It has 1 turning point at its vertex. But it could have up to 3. And like a 6th degree polynomial could have up to 5 turning points. A 12th degree polynomial could have up to 11 turning points. This one was a 4th degree. It had 3. Could have had less. Couldn't have had more. That'll be the end of this video and this section. Next time we'll come back and talk about rational functions. So I know you might be thinking, we just introduced polynomial functions. Why are we skipping to a different class of functions already? Well, rational functions are very closely related. We're going to spend the next 3 sections actually talking about kind of related things to polynomial functions, and then we're going to come back and talk about polynomial functions again in the last 2 sections of the chapter. So that's what we do next time. Hope you enjoyed the video. See you in the next one. Have a great day.